Here we have a fifth video of 6 related to a lab on studying permanent magnet DC motors. We talked about modeling the motor, developing torque speed curves, how we drive the motor using an H-bridge. Also, now we want to talk about making measurements of the shaft speed, and very common to use an encoder for this. I've put on the slide here just to point out that there are a couple different kinds of encoders and a basic operation. The idea is to have some kind of a signal, let's say an optical signal here, that passes, through, say, holes in a disc is a kind of classic. And what as this thing is rotating, as this disc is rotating, you can measure in a receiver the pulses, and by knowing the distance between these holes, you can say something about how many divisions you have, say, in a rotation. So you might actually have designations for encoders that are like how many pulses per revolution you can expect. Tells you how many lines or how many holes there are in that particular type of encoder. Incremental encoders work this way, and so they're okay for measuring speed, because all you have to do is then you have to measure the period, and you can allow timers to do that, to measure those digital type signals, right? You're not going to measure this with an analog A to D converter, for example. You're going to let timers do this, and there's some nice routines available, say, using an Arduino for doing this. That's discussed in some links to some resources on how to do this with an Arduino, and there's some code that we'll make available to you for doing that. Other types of encoders, called absolute encoders, might have some coding on the disks that so you're reading actual almost direct positions based on digital code on these disks, and so these are useful for measuring positions, whereas incremental encoders most commonly to measure velocities, because all you're having to do is measure the time between pulses, and you can discern then speed of rotation. Again, the higher the PPR, the better resolution you get, and so there's a cost for how high. You might see some as low as 12, which is the type that we have on this really cheap little motor that we're using, but you could see these go up to 1024 or sometimes 4096. And so these are optical encoders. Another very common type is magnetic encoders, which actually is the type that you find very commonly in these low-cost motors. They cost a lot less than optical types. They're compact. They use Hall effect sensors to pick up changes in the north-south type poles on magnetic pieces. And so these, if you think about it, are very easy. You just put a little permanent magnet, put a Hall effect sensor there, and you can pick up pulses. And a lot of wheel speed sensors and so on work this way. There's even integrated circuits now where you can position a magnet to rotate above it. Very compact designs. These are used in a lot of high-end control systems. A lot of signal processing then goes into these integrated circuits that allows you to do a lot of very sophisticated analysis, right? One particular encoder that you can find, I'm actually linking to one particular product that used to be available on Polulu. I don't know if it's still there, but this little encoder kit that you could buy and attach to a motor, on the order of $9. So it's a pretty low-cost encoder. You can see there's 2 Hall effect sensors here. You're monitoring basically the pole pieces on a little magnetic disc. And what's interesting is that the particular sensor that we have on this hobby motor is a very similar type. These encoders also have 2 channels, so you can, you basically building what's called a quadrature encoder, and so you can actually measure not only speed in one direction, but you can also you can measure speed, but you can also discern the direction based on the phase between the 2 signals. And again, there's algorithms for doing that. Not necessary for you to go into too much detail on that, and you can see how what you have to do is look at each channel to see how they're out of phase to determine which direction you're going, right? Pretty amazing. What I was going to say is like this little hobby motor that we use has an encoder. The whole package is $5.95, and you saw that this encoder on its own is almost $9. So it's a pretty nice little package to have this encoder packaged with a motor for our use in the lab, which is why I like to use it. I was kind of showing you how looking at the two signals from the two channels of this encoder. Here was counterclockwise operation, and you can see that channel A, you know, the difference between channel A and channel B. Here the green is, I guess you could say, is leading, and if you're going clockwise, you can see how, right, that, you know, the channel A is, or channel 1, sorry, is leading. So that's how you look, and what the algorithms do, you know, timers and so on, can look for these transitions, and in that way discern the direction of rotation. Okay. These types of really simple encoders, and especially magnetic encoders, easy to package. You find them in all kinds of, as I said, like tooth wheel applications. Again, you have two, maybe you might have a ferromagnetic wheel. You might have two magnetic probes inducing a magnetic field that you can then pick up with Hall effect sensors. You see these also in flow rate sensors. Here's a turbine flow meter that you might be, you might have a magnet embedded in one of the blades, and you're picking up pulses, and actually you see this in some really low cost flow sensors. These are little turbine type flow sensors that are really neat, and I don't know if I have where the, here's the turbine, and I believe this guy right here has the magnetic pole pieces, and again, it got a magnetic Hall effect sensors that can pick up the rotational rate, and in that way, given the number of vanes, you can you have a Q sensor, right? So same kind of algorithm that we're using to measure, say, speed of rotation for the motor can be used to measure and estimate flow rate using these simple sensors. They're used in all kinds of applications for like water dispensers and so on. In the next video, I'm going to just wrap up and talk about what you're going to walk away with from this.